Good day everyone. This time we'll look at the tube mill, a finished mill in this case. We usually do not pay much attention to the system, thinking that as long as the mill turns, all is fine. Yes, we check and correct the SO3 content, and of course adjust the separators to get the correct cement fineness, and that's it. A lot can be done to optimize the mill system, in particular for the sake of reducing consumption of the very expensive kilowatt-hour per ton of cement. This short video mainly addresses the influence of mill liners on the movement of the grinding media. In case of requiring specific assistance, please drop me a note in the video description below. Our specialists will come back to you. Let us strip down our system from feed to discharge to dusting, drive. And yes, without drive the mill will stop. The mill lining system is in place for two reasons: to preserve the mill shell from deterioration caused by the mill charge, and for lifting and turning the mill contents to grind efficiently. This example deals with typical lifting liners in the first mill compartment for coarse grinding. Liners are made out of high wear-resistant steels or pressure-molded rubber, sometimes with ceramic composites. These are lighter, enabling hand installation and generates reduced noise levels for improved working conditions. Manufacturers offer different liner profiles. Their support is key to select the right liner design and depends on the correct geometry angles, the mill speed, the grinding activity required, and the properties of the grinding media. Going back to our lifting liners, the logical question would be, what is the correct direction of rotation? One may be tempted to think that the edge side of the plates would do a better lifting effect, but then the edge would get broken and worn down in no time. The lifting plates act like a shovel, with a smooth release of the ball charge as the mill turns, limiting the wear and risk of plates breakage. We see what happens with new liners with a high lifting profile. To get a simpler view and better understanding in these simulations, I used a single ball. The mill is turning at 70% of its critical speed at around 13 RPMs. We see a nice lift of the ball on the liners, producing the so-called cataracting effect. Imagine the grinding media and material, here represented in green. The ball's impact zone is at the so-called toe of the grinding media, falling onto the material bed. The mill should not run without feed, otherwise the balls would fall directly against the liners, causing excessive wear and possible breakage. It is also important to check and refill the grinding media to keep the correct filling degree, thus to have sufficient toe and avoid the damages mentioned above. It is simpler and cheaper to refill the ball charge than to change liners. As liners wear off, the grinding media does not get so high in the tube mill and fall before the toe, reducing the grinding effect. The difference is noticeable when running these two examples side by side. A reduced grinding efficiency means higher returns from separators, regrinding of the product, and increased specific electrical energy consumption. The situation becomes even worse with liners having lost all their profile. Deciding when to change the mill liners should be planned according to cement stocks, the market demand, and analyzing all costs related to replacing liners against the inefficient process and increased manufacturing cost. I shall stop here for now, reminding you that optimizing the milling process is more than just checking wear on lifting liners for coarse grinding. Feel free to comment or ask questions in the descriptions below. We shall come back to you with alternatives on how to improve your grinding system. Thank you for your attention, and till next time, bye for now.